Okay, welcome to your second video lecture in section 10.1 on two-point boundary value problems. The examples in the previous lecture illustrate that there is the same relationship between homogeneous and non-homogeneous boundary value problems as there is between homogeneous and non-homogeneous linear algebraic systems. So it leads us to look for more similarities between boundary value problems and algebraic problems that we saw in Math 309. And another similar type of problem is an eigenvalue problem. So remember what an eigenvalue problem was in Math 309. Lambda is an eigenvalue of a matrix A with associated eigenvector V if AV is equal to lambda V and V is non-zero. In this lecture, we're actually going to consider the following differential equation: y double prime plus lambda y is equal to 0, with y of 0 is 0 and y of pi is equal to 0. Because both lambda and y are unknown, this is an eigenvalue problem as well, and it's an eigenvalue boundary value problem. For the eigenvalue problem, solutions are going to be pairs, much like in linear algebra, of lambda and y, where lambda is, of course, an eigenvalue, and y is an eigenfunction. To find these pairs, we have to consider three important cases, which is the difference between eigenvalue boundary value problems and eigenvalue problems in linear algebra. The first case that we have to consider is that lambda is 0. If lambda is 0, then we have this pretty simple boundary value problem where the second derivative of y is 0, and y is 0 at two different points. And the only function that does this is the function y is equal to 0. And since we're looking for non-trivial solutions, lambda equals 0 is not an eigenvalue. The next case we'll consider is when lambda is negative, and we'll denote it by negative mu squared to make our calculations a little easier. In this case, our boundary value problem becomes y double prime minus mu squared y is equal to 0. With the same homogeneous boundary conditions, the solution of the characteristic equation in this case is mu and negative mu, so our general solution is a couple of exponential functions, and the only way that these exponential functions can satisfy these boundary conditions is if either both of the constants are 0 or mu is 0, and neither of which we are considering. We're considering a negative mu, so mu can't be 0. And if both of the constants are 0, then y is 0. And so therefore, our problem does not have negative eigenvalues. Okay? So our final case we'll consider are positive eigenvalues. So we'll consider the case where lambda is equal to mu squared. In this case, we have the same differential equation as the previous slide, except for it's y double prime plus mu squared y is equal to 0, which gives us the general solution, the linear combination of sine of mu x and cosine of mu x. The first boundary condition, where we plug in 0, is going to give us 0 is equal to c1 times 1 plus 0. This is going to mean that c1 is 0. And the second boundary condition tells us that 0 must be equal to c2 sine of mu pi. Again, we don't want c2 to equal 0, so we're going to insist that sine of mu pi is equal to 0, which means that mu has to be an integer. Okay? If mu is an integer, that means each lambda is the square of an integer. Okay, so 1, 4, 9, 25, they all work. Okay? And the eigenfunctions are going to be associated with those are going to be y1 is equal to sine of x, y2 is equal to sine of 2x, and so forth. And so in this case, we actually have infinitely many eigenpairs, which is a bit different from Math 309. A matrix that's n by n has n distinct eigenvalues, possibly, but not anymore. Here we're actually going to have infinitely many eigenvalues and eigenfunctions. Okay, so that's one difference here. And one last thing to leave you with, in the case where we actually have y of L and not y of pi equal to 0, the eigenvalues in this case are actually just a bit different. It's n squared pi squared over L squared. And the eigenfunctions are sine of n pi x over L. Okay, so in the case where L is pi, the pi's cancel nicely here, and you just have lambda n is equal to n squared and yn is equal to sine of nx. But those are the general cases, and that will come in handy a bit later. Okay, thank you.